Hi, I'm Jim Burnham. Welcome to Chapter 14, Chemical Trends or Chemical Periodicity. In our last chapter, we talked about the evolution of the atomic model, from Dalton's bowling ball spheres to Schrodinger's cloud or quantum mechanical model. And that talks about how the electrons are arranged in orbital clouds. Well, in this chapter, we're going to follow that up and talk about the properties of elements in various groups in the periodic table and how those are based on those common electron configurations. We're going to see the utility and the beauty and the power of the periodic table as we look at periodic trends as well as group trends. Periodic trends are going to be the trends as we go across periods, horizontal rows, and group trends are as we go down groups or families. So let's talk about the periodic table again. In the last half of the 1800s, interest in chemistry was exploding. Chemical production was exploding. Things like fertilizers were being built, and bleaches, and glass blowing, and dyes, and soap making. And to help organize all of these new discoveries and the properties of these elements, the Russian chemist Dimitri Mendeleev devised the periodic table in 1871, and this was a monumental achievement. The periodic table is possibly the most important tool in all of chemistry. Now, do you remember how Mendeleev arranged the elements? You might remember he arranged them by increasing atomic mass so that elements with similar properties wound up in the same columns, and we still use a version of that today. This was incredibly useful for understanding and predicting the properties of the elements because these properties repeat. This is known as the periodic law. So it just says when we arrange the elements by order of increasing atomic number, Mendeleev did it by atomic mass, we do it by atomic number, which is very close. There is a periodic repetition of their physical and chemical properties. So as we move from across a period, there's a change of property. But as we move down, we're going to see those properties repeat. So in the first row, for example, the reactive metals, they all react explosively with water. And when you get back to that row, same thing. Every element in that column, in that vertical column, we call that a family, they all exhibit similar characteristics. And that's based on their similar electron configuration. They all have the same number of valence electrons. They have one valence electron in their s orbital. So, quick review, we call vertical groups families. This is the boron family. We call horizontal rows periods. So this is the fifth period. This would correspond to the fifth energy shell. And if we know the physical and chemical properties of one element in a group, then we can make a very good guess about the physical and chemical properties of other elements in that same group because they all have the same valence electrons. We could even start making guesses about elements in neighboring groups. So we already know the elements are arranged in order of increasing atomic number. And so we're going to now relate that to the electron structure and the periodic table. And we're going to see various trends that emerge as we look at the periodic table and examine the elements. So first, let's review classifying elements by electron configuration. Well, there's four basic categories. The noble gases, these are the row 8 or sometimes row 18. They all have complete shells, complete S and P shells, and so they're not looking for any electrons. They're very, very stable. They're chemically inert. They make very few compounds. So that's row 8, the noble gases. Interestingly enough, if you pass electricity through gas, any of the noble gases, they make these awesome different color neon lights. This is what neon lights are made out of. The noble gases are characterized by having a full valence shell of 8 electrons. So neon has 8 electrons. Argon, in its outer shell, 8 electrons. Krypton, outer shell, 8 electrons. We know that that corresponds to a S2 shell and a P6. And when those are filled, then they have no desire to change. They're complete. So if you look at all the noble gases, you're going to see, with the exception of helium, which only has a filled S2 shell, all of these have 8. And that's what characterizes them. Again, another way of depicting their electron shell arrangement, and you notice that the outermost shell, with the exception of helium, has 8 electrons. That takes us to the second group, the representative elements. These are the ones in green here. We call these the representative elements. Oftentimes, the noble gases are included as part of the representative elements, but sometimes they're defined slightly differently. Sometimes representative elements are defined as having partially filled S and P shells. When you get over here, these are fully filled S and P shells. But in any case, these are all the representative elements, and they are characterized by having S shells and some number of P shells, including fully filled P shell in the noble gases. So outermost S and P sublevels partially filled, if we exclude the noble gases. Another way to look at it, so we call this the S block, and this is known as the P block. And so the representative elements are the S and P blocks. The group number tells us the number of valence electrons. So if we go back to this, we can see this is group 1A. A just means they're the representative elements, as opposed here to the transition elements. These are group B. And 1, that tells us that has 1 valence electron. 1s. So these have an S1 outer valence electron. These have an S2. These have a P1, and that tells us, so if you add those together, we have 3 valence electrons in the boron family, 4 valence electrons in the carbon family, 5 valence electrons in group 5, the nitrogen family, 6 in the oxygen family, group 6, 7 in the halogen family, group 7, and group 8, as we mentioned, totally full. Next, or the third group we're going to talk about, are transition metals. This is known as group B, also known as the D block. As we saw here, that's this group here, this rectangular group in between the S block and the P block. And these are characterized by having their outermost S and D sublevels with electrons. Remember, representatives were S and P, transition metals S and D electrons. And finally, the fourth group, we have the intertransition metals, also known as the F block. And here they're characterized by having their outermost F and S sublevels with some electrons. And so that's the F group down here, which is a sublevel of this D block, this transition metals. This D block is called transition metals. The F block is called the inner transition metals. Another way of depicting this, you can see, now so this is with the electron configuration. So if we went through here, 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. And that's full. So we start over. 3s1, 3s2, 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. Now it's full. We start over with 4s, 4s1, 4s2. Then we jump back to the 3ds, fill that out, and then we get back to the 4p's, and so on. So we can build up the entire periodic table, electron by electron, with these increasing energy shells, which are shown by the increasing rows, and by increasing orbital by orbital through the S block, the P block, the D block, and then the F block. This is the periodic table in long form, where we put the F block, where it really is, in between here in the D block. We rarely see this because it makes it so long. So we usually break that out and put it below. But here it is in its full unchanged glory. So again, this is just showing how we describe the electronic configuration of various atoms as we go orbital by orbital, electron by electron, through their configuration. So nitrogen, as we've seen, is 2s2, 2p3. Nickel, 1s2, 2s2, 2p6, 3s2, 3p6. Then we have 2s2 and 3d8. Some important families of the periodic table. You already know that basically everything here on the left, with the exception of hydrogen, are metals, and everything along this stair step are metalloids, and everything here on the right are nonmetals. Group 1 are known as the alkali metals. They are the most reactive metals. You almost never find them alone, but always with just some sort of compound. They form +1 ions because they like to lose that one electron in their s orbital, that one lone electron in their outer shell, the outer valence electron. They like to lose that to get back to the noble gas configuration. So they love to become a +1 cation. Those are the alkali metals. Next to them, group 2 are the alkaline earth metals. They are called alkaline because when they react, they usually produce a base. They're like group 1, always found in compounds. They like to lose 2 electrons because they have 2 electrons in their outermost s shell. And so when they lose both of those, they get back to the electronic configuration of the nearest noble gas. The transition metals, they have all the properties of metals, but they're not as reactive as groups 1 and 2. The boron family likes to lose 3 electrons. It's group 3, has 3 to lose, loses all 3, goes back to the electron configuration of a noble gas. The carbon family can go both ways. It'll either lose or gain 4 electrons to become like a noble gas. Nitrogen family wants to gain electrons. It wants to gain 3, and then it becomes like the nearest noble gas. Oxygen family wants to gain 2. Halogens want to gain a single electron. They're very reactive. And interestingly, whenever a metal and a halogen combine, they form what's known as a salt. We already should know this because sodium chloride, one of the most famous combinations of a metal and a halogen, is known as table salt. The noble gases, as we said, are very unreactive. Their outer orbit is full. Now let's get to some periodic trends. These are overall trends that we should be able to identify in the periodic table. And just like families have similar physical characteristics, elements in chemical families also have similar chemical and also some physical characteristics. So you look at this family, nice family here. They have the same kind of smile. They all have blonde hair. You can see a lot of similarities. What trends do we see among the families and periods of the periodic table? Well, we're going to see 4 basic trends. Atomic size, ionization energy, which we'll define in a second, ionic size, that's when an atom gains or loses electrons and becomes either bigger or smaller, and trends in electronegativity. So here's some definitions. The size of the atom, the ionization energy, the energy required to steal an electron, to remove an electron from an atom, and electronegativity, the tendency for an atom to attract electrons to itself when it's chemically combined with another atom. So trends in atomic size. Well, if you look here, they've picked cesium to be the largest element. It is in this here, and then they've made every other size relative to the size of cesium. And as you can see, everything that isn't cesium, right, is smaller. And you can see this trend that even along a row, the atoms get smaller and smaller and smaller. So cesium is the largest element, at least in this chart, and helium is the smallest. And so if you had to draw an arrow describing this trend, you would say that as it goes this way, the atoms get smaller. Or if you want to describe it the other way, you'd say they get bigger as you go down and bigger as you go to the left. So you draw the arrow the other way. So here's a great example. It's just this decreasing size as you go across the row. Here's another depiction of this, and again you see decreasing size as you go to the right, increasing size as you go down. So it's important to remember that you're beginning, so francium here would be the biggest, helium here would be the smallest. So if you drew an arrow, you would get the right trend as things get smaller. Again, another way of showing the same information. So let's examine group trends. These are trends along the same vertical family. the atom size increases as you go down a group, as we see over and over again. Okay? This is bigger, so as you go down, bigger, 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 bigger. Why does that happen? Well, as we go down the successive periods, we are adding electrons to higher principal energy levels. So we're adding energy shells, energy clouds. Each row has another energy level added to it. But at the same time, we are also increasing the number of protons and neutrons in the nucleus. So two things are happening. We're adding shells and we're adding protons, and they work in opposite directions. So here's showing how we add shells. I don't know if you can see this. This has a single shell S. This has a double shell, triple shell, 4, 5, 6, and ultimately 7 shells. And every shell is further away from the nucleus than the shell before. But that nucleus is getting bigger and bigger and bigger. So you'd expect the nucleus to be exerting more attraction because it has an increasing nuclear charge. But you would also expect the shells to be getting further and further away, and so feeling less of that nuclear charge because of increasing distance. And so which wins, right? You have two competing forces. You have increased nuclear charge, which is like a stronger magnet, and you'd expect that to pull on those outer electrons and shrink the atom size. But you also have increasing distance from the nucleus, which creates less pull from the nuclear charge. And in this case, the greater distance overcomes the greater magnet. And therefore, atomic size increases with the addition of successive shells because the greater pull is defeated by greater distance. But that doesn't happen within a period, within the same horizontal row. What happens is the atomic size decreases as we go. Why? For the exact same reason. Every time you add another electron, you add another proton, a neutron, and so the nuclear charge gets stronger and stronger and stronger. And those, every time we add an extra electron, it doesn't go into another shell, it goes into the same shell. So it's the same distance away as every other electron in the shell. So it doesn't have increased shielding or increased distance. So the increased nuclear charge pulls that shell closer and closer and closer together. And that's why you see the decrease of the size as you continue to add electrons and protons. So as we go across a period, the principal energy level remains the same, but there are more protons, and those protons pull harder on those electrons. So same energy level, but increasing nuclear charge. The greater magnet pulls those electrons closer and closer and closer together as you march across. This is just another way of showing the effect of increasing nuclear charge. So here's beryllium and oxygen. They're both on the same energy level, but oxygen has more neutrons and protons, so it pulls harder on its outermost shell of electrons, and therefore its net size is smaller. So here's another way of showing. So as we go from lithium has 3 protons, beryllium has 4, 5, 6, 7, 8, 9. And as we increase the number of protons, we're going to decrease our atomic radius because it is the nuclear charge, the increasing nuclear charge is pulling harder and harder on those outer electrons. This also explains that one of the next things we're going to talk about, ionization energy. That's the energy it takes to steal an electron. Obviously, it's going to be harder to steal an electron from this fluorine, which is more tightly packed, than it is to steal an electron from lithium. So, the effect of increasing nuclear charge is to pull them closer to the nucleus. And if we graph this, you'll see this. Every time we start a new period, they're bigger, and then so here's group 1, group 2, and as we go down, they get smaller and smaller until we get to the noble gases. Restart the group, smaller and smaller and smaller until we get to the noble gases. Group 1, group 2, smaller and smaller and smaller until we get to the noble gases. So you see this very, very obvious pattern of decreasing atomic size as we increase the nuclear charge across a period. Now let's go to the second trend, trends in ionization energy. Now when an atom gains or loses an electron, we know that it becomes an ion. Gaining or losing electrons changes the electric charge. So here's sodium atom becoming a sodium ion. It loses its outermost valence electron. It likes to do that. And then it forms this more stable octet by getting rid of that ion. The opposite happens over here. Chlorine has 7 electrons in its outermost valence shell. It wants one more electron to become like the noble gas. So it loves to take that electron from sodium and add it to its shell, and it becomes the chloride ion. And as you can see, we'll talk about atomic size, this is going to make the sodium ion smaller because it's losing a shell. This is going to make the chloride ion bigger because it's gaining an electron. Well, it takes energy to overcome the attraction of the nuclear charge and to take an electron from the atom. So it takes a certain amount of energy to pull that electron away. And that energy to remove a mole of electrons from a mole of gaseous atoms is defined as ionization energy. Removing one electron forms a positive ion, cation, and the energy to remove that first outermost electron is, unsurprisingly, called the first ionization energy. So here are the ionization energies it takes to take the first electron away from these various elements. And as you can see, it's very difficult to take them from these smallest noble gases. So this chart is almost the reverse of our atomic radius chart. And it's because the energy to pull them from these tighter, smaller atoms takes more energy than to take them from these big fat atoms. So here are the big fatter atoms, right? The energy it takes to pull an electron from them is a lot less than the energy it takes to pull one from the noble gases. To remove a second electron from a gaseous +1 ion requires even more energy than the first ionization energy, and that's called the second ionization energy. Third electron, third ionization energy, and so on. So if we plot this, you can see, looking here at sodium, the energy it takes to take that first electron away is around 500 kilojoules per mole. But look at the energy it takes to take another one. It jumps dramatically. It's almost a 10-fold jump in energy. Look here, and that makes sense because this has a single valence electron. Pulling that away doesn't take as much energy. But now you've got to the core electrons. And when you see that jump between the lower energies and the higher energies, that tells you the number of valence electrons. And it tells you what group it belongs to. You have one easy electron to grab. That means it's group 1. Here you have 2 easy electrons to grab before you get to this high energy jump. Here you have 3 electrons you can get before you have this massive energy jump. In silicon, you have 4 easy electrons before you get to the massive jump, and that corresponds to silicon's 4 valence electrons. Okay, phosphorus has 5 before you get to its jump. It has 5 valence electrons. Sulfur has 6, and you can see it has 6. Yeah, these are increasing, but not as dramatically as this jump between, say, 8,000 and 28,000. Right? Chlorine has 7, and then argon. They're all hard. But look, so you can see as you go across, it gets harder and harder to take away the electrons because they are smaller and closer to the nuclear charge. So we can use this concept, as I just did, to predict ionic charges. You would say, yeah, this has 1. This would make a +1. This would make a +2, +3, +4, or -4. This has got 5. This is going to make a -3. It's going to want to gain 3. This is going to want to gain 2. This is going to want to gain 1. And this is not going to want to gain anything. So we simply look for the large energy jump between the easier to remove valence electrons and the much harder to remove core electrons. The number of easier to remove electrons equals the valence electrons. Okay, what about group trends? That's going vertically now in ionization energy. Well, as we can see from the table, the first ionization energy generally decreases as you move down the group. So it becomes easier and easier to pull off this outermost electron. Why? It's further away. Same thing, it becomes easier and easier to pull off this electron, and so on. So you generally see this decreasing ionization energy as these atoms get larger with successive energy levels. It becomes easier and easier to remove that outermost electron. So here it is in kind of 3D form, the first ionization of the main group elements. And as you can see, they decrease as you go down the rows. Why? Well, the size increases as we go down because we've added additional energy shells. The electrons are farther from the nucleus, experiencing less pull. So it takes less energy to extract them because they're being pulled by the nucleus. There's less nuclear charge. Remember, extra shells, further away, easier to remove. And therefore, a lower ionization energy. But if we go to the right, the energy it takes increases. Why? Well, because the effective nuclear charge increases. The same thing that makes the atom smaller makes it harder to pull an electron away. So the ionization energy generally increases as we move left to right because of the increased nuclear charge, but no additional shielding. So the magnet gets stronger and they just get closer and closer because of it, and thus harder and harder to extract. So if we looked at ionization energy, okay, it increases as we go up because they're smaller, and it increases as we get closer to the smallest atoms. So this chart is basically the inverse of size. Now let's talk about trends in ionic size. This is the third thing, and this is going to be very similar to trends in atom size, as we're going to see. So we know that atoms of metallic elements have low ionization energy. That is, that it doesn't take a lot of energy to form positive ions. They form those very easily. I like to call the metals losers and the non-metals winners. Metals are losers. They like to lose electrons. Yes, it does take a certain amount of energy to extract them, but a lot less than the non-metals. By contrast, the non-metals are the winners. They love to grab and hold on to electrons. So they're the takers, metals are the givers. What effect will losing or gaining electrons have on ion size? Well, it's kind of surprising. Look at the relative size of some of these ions compared to their parent atom. So here is a neutral lithium atom. It has a size of 152. And here is the lithium ion. So we've lost a single valence electron in the S shell. And the size has basically been cut in half. It goes from 152 to 60. Look at sodium. It goes from 186 to 95. Loses a single electron, its size is nearly cut in half. By contrast, look at chlorine. Starts out at 99, it gains a single electron, say from sodium, and it nearly doubles. So you're going to see this pattern where cations are generally around half the size of their parent neutral atom, and anions are about twice the size of their parent atom, neutral atoms. So cations are smaller than their starting atom, anions are bigger, almost double. Let's look at group trends referring to ionic size. We know that positive ions will always be smaller than their parent atoms. And this is because they lose their outer shell electrons. And so what's left? Well, then what the remaining electrons experience increased attraction by the nucleus for the fewer remaining electrons, effectively making it a greater magnet. And so they get pulled dramatically closer, not just a little closer. Their size reduces by about half. So like atomic size, ionic size increases down a group because we're adding energy levels which are further away from the nuclear charge. So ionic size is going to follow the same exact pattern as atomic size, with one big exception. So lithium is going to be smaller than beryllium, which is going to be smaller than boron, which is going to be smaller than carbon. But then, so these are cations, but then these are going to be bigger, right? Because they're anions, right? These are going to be cut in half, and then from that point get smaller. These are going to double, and then from that point they're going to get smaller. So it's just like the atomic size, except you have a reset here as you get to the anions. They're going to start bigger and then follow the general trend of getting smaller as we go across the period. So they decrease across a period, then they jump in size at nonmetals and then continue to decrease. And they all increase on the way down because we're adding extra energy levels. So this is exactly the same chart as atomic radius with this one little break, because this break is where the anions begin. They start larger, but then they also decrease. So here's the key concept when it comes to ionic radius. Cations, always smaller than their parent atoms. Anions, always larger than their parent atoms. They both follow the same pattern as atomic radius. They get smaller as you go to the right. They get larger as you go down. So which is larger? The anion is larger. Okay. Which is larger here? Sodium or magnesium? The sodium is, because this is further to the left. This is more to the right. It's going to get smaller. Let's look at the last trend, which are trends in electronegativity. We define electronegativity, as I said, the tendency of a bonded atom to pull or attract electrons to itself. Think of it this way. In every bond, atoms play a tug-of-war, trying to pull the electrons to themselves. And the most electronegative atom wins. The more electronegative it is, the more it pulls the electrons to its side. So we've calculated electronegativities for the elements, and we express them in arbitrary units called the Pauline scale, the Pauline electronegativity scale. And in this scale, now they have no units, it's just relative. What they've done is they've set the most electronegative element, fluorine, at 4, and then everything else is set relative to that. So fluorine is the most electronegative element, and cesium on this chart is the least electronegative. So this goes from 0.7, tendency to pull electrons to itself, to a 4. So you can see, just like ionization energy, the trend goes from cesium to fluorine. Notice where are the noble gases? The noble gases don't appear because they do not have this tendency to pull electrons to themselves. So we leave them out of the discussion on electronegativity. Okay, so here's a chart that has francium, same thing, 0.7 all the way to fluorine, 4. Leave the noble gases out because they don't form any compounds. Again, we see the same pattern where we start here at the bottom left and we move to fluorine, increasing electronegativity. It goes down a group, but it increases left to right. Cesium is the least electronegative. Here's the important one to remember. If you just remember one thing, remember this. Fluorine is the most electronegative. So as elements get closer and closer to fluorine in the periodic table, they get more and more electronegative. Just like this girl is going to easily overcome the pull of this girl, this is fluorine. Fluorine is the winner. Fluorine's electronegativity is so strong, when it is bonded to any other element, it either pulls the shared electrons to itself, or it outright steals them to form a negative ion, a fluoride ion. So, most electronegative element is fluorine. If you remember that, everything else becomes easy because everything increases as you get closer to the most electronegative. What's the practical payoff? Well, electronegativities allow us to make predictions about what kinds of bonds will form between different kinds of atoms. Is it going to be a covalent bond? Is it going to be where they share atoms? Is it going to be an ionic bond where the most electronegative element has stolen the electron? So putting it all together. Oh, this is my little.
Who are you? Are we enemies? Why am I on this wall? Where's Buttercup? Let me stay. No, there is too much. Let me sum up.
To sum up all of our periodic trends, and again, this is our key concept. Atomic radius, it's going to increase as we add shells, but it's going to decrease because of increased nuclear charge. That's going to be the same thing that we see with our ionic radiuses. The radiuses are going to decrease as we go to the right, and the anions are also going to decrease. They're going to increase initially, but then also decrease as we go to the right. Both are going to increase as we go down. So atomic radius and ionic radius are virtually the same, except for this anion reset as we get to the negative ions. Ionization energy is going to decrease as we go down because the atoms get further away from the nuclear charge, but it's going to increase as they experience greater nuclear pull, the effect of the greater nuclear magnet. And again, electronegativity, just like ionization energy, is going to decrease as we go down and increase as we get closer and closer to fluorine. So I'm going to put all this together here. What we see as we go across, nuclear charge increases because they're in the same energy shell, but we get more and more pull from the nucleus. Their shielding is constant, so they're not experiencing any shielding or any further distance from the nuclear charge. So that's why the atomic radius decreases. That's why ionization energy increases. And that's why electronegativity increases. Looking this way, the nuclear charge increases, but so does shielding and distance. So the atomic radius is going to get bigger. The ionic size is going to get bigger. The ionization energy, the energy it takes to steal electrons, is going to decrease. And we see decreasing electronegativity as we move towards francium, the least electronegative, and increase as we get closer to fluorine, the most electronegative. Again, we don't include noble gases in discussions of electronegativity. Another way to summarize all the trends: electronegativity increases this way, decreases this way. Ionization increases this way, decreases this way. Atomic radius decreases this way, increases this way. Nuclear charge increases this way, also increases this way. Shielding is constant in this direction, but it increases with increasing distance as we go down. And then here's this super chart. Might be good to have something like this in your notes. And this summarizes basically all the major trends of the periodic table. All right, we can check for understanding which of the following atoms has the largest atomic radii, ion size, electronegativity, and ionization energy. And I will leave that to you to figure out. I've circled here which ones they are, but you need to be able to pick them out. So for example, if we were looking at atomic radius, we would say this is has a bigger radius than this. This is going to get smaller as we go. So in this row, the smallest atomic radius would be chlorine. And that's the end. Thank you for your time.